Hello and welcome to today's Saratech Enablement session. My name is Andrea Hall and I am the Customer Relationship Manager at Saratech and I will be your host today. Presenting we have Kelsey Safar, who is an Applications Engineer here at Saratech, and she'll be talking to you about FloEFD for NX12. Our sessions run about 30 minutes each and are all recorded and posted to our Saratech YouTube channel. Make sure you check out our past sessions there. Twice a month, we meet right here to learn about tips, tricks, new and old features that will help you with your everyday tasks. This is an open forum, so if you have any questions or comments during the presentation, please type them in the chat box or the questions box over to the right-hand side, and I will kindly interrupt Kelsey and let her know about your comments or questions. And with that, I'll pass the baton on to Kelsey. Thank you.
Hi, everyone. My name is Kelsey Safar, as Andrea mentioned. I've been with Saratech for about a year now, and I am an applications engineer. And maybe you have been in contact with me if you've ever filled out a case with us before. And so the few things that we're going to go over is what exactly is FloEFD, why front-loading CFD is important. We're going to go over a demo and then go over a case study. So, what is FloEFD? Well, it's an award-winning MCAD computer fluid dynamics simulation tool that is embedded within NX and Solid Edge. NX is on the left and Solid Edge, the interface, is on the right, and it can compute fluid flow and heat transfer analysis. And like I mentioned, it's fully enveloped within the design environment, which allows for really great front loading with the simulation process all throughout the manufacturing process. So why is front-loading CFD important? Well, it reduces the simulation workflow by as much as 75%, and the closer you get to moving the simulation to the concept part of the manufacturing process, rather to production and maintenance, it really reduces cost and it saves a lot of headache. So a couple things that we're going to go over in the demo. We're going to learn how to do a project setup. We're going to check the geometry for our fluid flow. We're going to go over a lot of plots. So some of them are cut plots, surface plots, and flow trajectories. So the flow trajectory is actually the picture that you see. And then we're going to go to the XY plots and goal plots. And it's all going to be embedded within NX12. So going through NX12. So here we have, we're going to do a flow-only program, and it's very simple. It's going to be a water analysis, and we're going to be applying the analysis to this quick release valve. As you can see here, there's about 22 parts. So we're going to clip this right here, and then we're going to show the cross-section. And right now, we are currently just simply in the NX environment. We don't have FloEFD up and running just yet. But I like to show that we do have two lids, lid 1 and lid 2. And usually when you're modeling, you wouldn't have these lids here. But for FloEFD, since we're doing it in internal flow, we need an internal flow cavity. And some of you may be wondering that there are, or noticing that there are a lot of internal overlap, and overlapping parts are fine for FloEFD. There's an option when you run the analysis to exclude internal cavities. So seeing these teeth and these overlapping parts is going to be fine for FloEFD. So to access FloEFD, just go down in the upper right-hand corner, upper left-hand corner, and the file going all the way down to all applications. And towards the right, we see simulation, and then we can just access FloEFD simulation. And another quicker way, a hotkey, is doing Control-Shift-F. And then we notice at the top toolbar, we see flow analysis right to the right of 3D connection, and then to the side left of the tabs are FloEFD as well. So going through, the toolbar is very accessible and it's user-friendly because if you ever get confused of what to do with a FloEFD analysis, all you have to do is know to go from the left to right. So before we do that though, we're going to check the geometry. We're going to check it and we see that it is successful, and we're going to show the fluid volume. So this is the expected fluid volume that the analysis is going to run through, and this is always highly recommended to view what the analysis is actually going to be running through. So we're going to select OK. Running to the front. And then now we're going to go to the toolbar. So the first thing that we're going to do is set up a project, or a second project. We're going to name this project 2, and so a couple options here. You can run configurations to the model. So if you have different configurations for a part or a family of parts, you can select that. Here we're just going to do the entire quick release valve. So we're going to hit select next. And then this is when we're going to set up our units. So we have a lot of different units in our system. English and metric, but we're going to choose USA predefined, and you can also create your own unit systems as well. So here we're going to change these this pressure unit to 2 decimal places, and then the velocity is going to be foot per minute. And the next thing we're going to change is going down to loads and motion. And the loads in motion is going to be, we're going to edit the volume flow rate. Instead of that, we're going to do US gallons per minute. So making sure it's US because there is also UK. So US gallons per minute. Okay, just going over everything else. That looks good. Select it. And then now we're going to do an internal flow. So you can either do an internal flow seen in the bottom picture, and then, or you can do an external flow, which is the upper picture. And this is what I was mentioning, where you can exclude the cavities without the flow conditions. And then we're not going to select any of these values because we're just doing a simple flow. Next. And the fluid that we're going to choose today is very unique. I'm sure maybe some of you guys have heard of it. It's water. So it's going to be an incompressible liquid of water, and you can also select or create a new fluid if you choose to do so. And there's also an option for cavitation, but since we're doing a simple fluid analysis, we're not going to do that. And we're going to keep the wall conditions as a default, and we're selecting the ambient pressure and temperature. So it's going to be room temperature and atmospheric pressure at sea level. So that all looks good, and we're going to finish. So if you notice, a black box has appeared around our model, and that is the computational domain. So that's the domain that FloEFD is going to run through, and we can hide it by right-clicking and selecting hide. So now that we've selected our wizard under projects, the next thing that we're going to do is insert boundary conditions. So there's a few boundary conditions options with porous medium, surface source, volume source, but we're just doing a simple boundary condition at the inlet. So here in this GUI, the first thing that we have to do is select where inlet's going to be. So it's always best practice to right-click and say select from list, because sometimes NX has a bunch of options when you select a certain surface, and we need to select the inner surface. So if you notice there's 2 different ones, make sure you select the inner surface. And let's see here. We are going to do a inlet volume flow of 10 gallons per minute. And we want to make sure that the flow is fully developed, so it'll be nice and parabolic when it comes into the inlet. So we're going to select that, and we notice that it's going in with the red arrows. And the next boundary condition that we're going to do is for lid 2. So it's going to be the same boundary condition option, but this time we're going to do a pressure opening, and the pressure opening is in between the flow opening and the wall. So this time we're going to do an environment pressure, but of course we have to select the lid. So right click, select from list, and then we're going to select the interface. And if you notice, it is at atmospheric pressure at sea level. So we're going to select OK. And then we notice that there's 2 arrows, and it's as if the lid doesn't even exist, and it's dumping it out at sea level. So now that we have that, we have our 2 boundary conditions. The next thing that we're going to do is under mesh option, we're going to do the global mesh. Oh, sorry about that. We're actually going to do the global goals because we need to figure out what we want the software to learn. So what we really want to learn from this quick release valve is what is the minimum pressure drop to maintain the flow rate of 10 gallons per minute. So the first thing that we have to do is set a surface goal. So in the drop-down menu, third from the top, we're going to select a surface goal of static pressure, but we don't actually need to select the inlet surface. We can just select inlet volume flow rate, and it'll recognize what surface it was, and we're going to do an average static pressure. And then we can even rename our goals. So we're going to rename it inlet P. And then we're going to select OK. So here we have inlet P, and the next one we're going to do is do an equation goal. And equation goal is the last one in the drop-down menu. And what we can do is make sure that you just select inlet P, and then minus, and then the environmental pressure. So select environmental pressure under boundary conditions, and then drop-down menu is going to be here. Just make sure that you press environmental pressure and add it to the formula, and then you'll notice that it's right here. Double check the formula, and then we're going to label as DP as change in pressure, and we are not going to use convergence control. So the CFD model, what is convergence control? The CFD model essentially runs through a number of iterations to reach a specific stable point where the flow is at equilibrium. And since this is an equation goal and the inlet P is at convergence, then DP doesn't have to be as well. So select OK. And Andrea, I think we have a question.
Yes, I was looking for a good time to interrupt you. So Chad wants to know what the difference is between the goal flag colors.
Great question. So if you notice under goals, we have inlet P and DP, and then inlet P is yellow and black, while DP is red and yellow. So the yellow and black contains convergence, while the red and black, the red and yellow does not. So like I mentioned, only one goal needs to be at convergence since DP is at equation, and since inlet P is at convergence, then both of them are going to be going to an equilibrium point. So yeah, great question. So the next thing that we're going to do is we're not done with our goals just yet. We're going to have to select a global goal. So one of the global goals that we're going to look into is the maximum velocity. So we might want to see where inside the model the fluid might be doing the most damage. So that would be a good point to reference. And we don't have to rename it. It'll just be global goal max velocity 1. And then we're going to do one more global goal, but this time this is going to be a force in the X. So if you notice that you have a whole bunch of options to record, but with this one we're just going to do a force in the X. And this might be helpful if you want to know the X directional force imported due to the water moving from the left to right. And in case if you wanted to put a clamp on this valve, you can understand the stresses and strains a bit more. So selecting OK. So now we have our goals. We did our boundary conditions. We checked the computational domain. And next, we're going to do the meshing. So there's 2 types of mesh. There's a global mesh, and then there's a local mesh. So local is for the more specific areas, while the global goal is for the entire computational domain for that entire section. So we're going to do a global mesh. And within global mesh, there is a few options, and FloEFD actually has a really great resource in the help documents. If you just select F1, it comes up through a whole list of explanations of going through the entire mesh settings. So if you're ever curious to know a little bit more about how meshes work, definitely I would highly recommend going to there. So for this, for an automatic, we are going to select 5. Actually, I'm going to show the basic mesh. So if you notice, at the lower refinement, the boxes get a little bigger, and in the higher refinement, they get, well, more refined. And the lower refinement, the quicker the analysis, but less accurate, and the higher refinement, the more the analysis will take, but it'll be more exact. We're going to select it as 5, and this will be our base mesh, and then we're going to select manual right beneath automatic, and then we notice that it takes the basic mesh of the 5, and then there's 2 other options, channels and advanced refinement. So channel is essentially, these 2 essentially refine the computation for the fluid between, well, the channels, so going through, if the fluid goes through these channels. And it also, the advanced refinement essentially goes through how the fluid is actually interacting with the solid. So this time we have a solid, but if you have a porous medium, it's how it intersects with the porous medium. So here we're going to change the level to 3. So this one is a characteristic, this one is, we're going to change this to 4. And that is the number of cells across the model's flow passage. And we're going to change this level to 3. And that restricts the size of the smallest cell. And then advanced refinement, we're going to all select these to 2. And so, for example, if there's like a curvature on the solid, it essentially changes how the software is going to interact. So the higher refinement, the more realistic the meshing will be, and how the software will analyze the project. However, it would take a little longer. So just checking our meshes here. It looks good. Oh, and we're going to hide the global mesh as well. So the next step is under the solve option. We're going to do run. And there's a few options while running your analysis. You can use the different types of cores for your computer. We're going to use all of them for our run. And you can run it to a different supercomputer in case you have a better computer. And then you can also close the CAD. So this can free up an NX license if analysis can take up too much time. So these are all very handy options, and I would highly suggest them.
Kelsey?
Yeah.
We have one more question from Robert. He said, is there a possibility to do multiple runs?
Oh, yeah, there definitely is. Right next to run, there are batch runs. So yes, the answer is yes. And FloEFD actually allows the user to select a lot of certain options depending on the project and run. So I can actually select it for you. So you have a bunch of options, whether you want to define a certain mesh for a certain project or the number of cores the computer uses, and so you can set up multiple runs. So yeah, great question. This time, we're not going to go through and wait for the computation. We have a project already set up. Usually this would take about 5 to 10 minutes. But we're not going to have that time. So I preloaded one for us. And some of them don't come loaded when you first run the project. So you can just right click and select load, and it'll load all the results. Or you can just go down to this drop down menu under results and do the same thing. So a couple things that we're going to go over. The first thing that we're going to review is the mesh. So we're going to right click and select show. Then we're going to de-highlight and hide the geometry so we can better see the meshing. So when we selected the global mesh as an automatic 5, this was our base mesh. It's level 0. And then the second refinement level is 1. So it takes the base refinement and splits it up into groups of 4. And then the second refinement level takes that 1 and splits it up into 4 again. And then the third one is just for the more refined spaces. So that's where the channel options and the advanced advanced refinement really comes into play. So that's that. Let me go here, show the geometry. Great. All right. Now we're going to hide our mesh and then go to cut plot. So these don't come loaded to basically lighten the NX load. So it's good practice to hide them and show them, but you can also show them both at the same time if you want. But for clarity, we're just going to do them one at a time. So if you notice, right when you select the velocity or the cut plot, it shows you the maximum. So if you want to hide the maximum, just go ahead and right-click and select Hide Plot Maximum. And if you notice, we had a lot of options that FloEFD catches: the density, the pressure, temperature. As you can see, we're going to go over the pressure first. So we noticed that as going through the inlet, the flow's pressure is around 25 psi, and it slowly goes down to atmospheric pressure. But if you wanted to know specific values, all you would need to do is select probe, and it's right underneath the flow analysis tab. Just go ahead and select it, and you can notice that the cursor goes into a probe, and we can select going through all our portions of our model, and then cleaning it up a little bit, we can, let me go back to that. We'll go here. We can notice the gradient of the pressure. So it's going from 25, and it raises a little bit when it goes to stagnation pressure, and this is when the flow gets abruptly stopped to 0. So that's where the stagnation pressure would be. And it slowly goes out to atmospheric pressure. And if this gets a little bit too clunky for you, all you have to do is go underneath probe, and you can delete all of them. So it cleans it out again. And then if we go back to velocity, we can see how quickly it changes as well. And you can see as the velocity increases, as the change of area decreases due to mass flow rate, and how it increases again as the channels get a little bit more refined. But we notice that the the velocity is around the same from the inlet to the outlet due to the mass flow rate. So another cool option that you can do is if you select cut plot, you notice that there is a box that goes around it, and there's a little arrow in the middle, and you can move it backwards and forwards. So not only can you see the cut plot of where you selected it, but you can actually see the flow as it goes from backwards and forwards. And not only that, but you can right-click and select play, and you can have a video of the cut plot going through your entire model from back to front, which I think is really cool. And if you ever want to stop the video, there's a little stop button in the bottom right corner of your computer screen, and there's also another option to right-click and say stop. And you can also export this to a video as well. So the next thing that we're going to do is show a surface plot. So we're going to hide this and go straight down and select show. And we notice that this is a velocity plot, so it's normal that the velocity is going closer to 0, or at this case, well, let's check what it's going at. So it's going around 21, it's the pressure. Let me delete all probes. Velocity.
Hey, Chelsea, while you're doing that, we have one more question from Dustin. He wants to know what is an ISO surface.
Yeah, an ISO surface. So we don't have an ISO surface. I didn't load one, but that's a good question. An ISO surface is a 3D surface created by, well, of course, FloEFD, and it essentially takes a specific variable that you choose. So if you selected something from the drop-down menu and wanted to know the velocity at, let's say, 30 feet per minute, then the FloEFD would create a 3D surface alongside where the fluid domain would be, and it would highlight wherever the 15 feet per minute fluid is running. So that's what an ISO surface is. Great. So if we notice, yeah, the velocity is going close to 30 feet per minute, and we're going to hide the geometry so it's a little easier. We notice that it is a nice parabolic flow, because as we go a little bit closer to the center, it is increasing in flow. And we're going to change this to pressure. And it's what we would expect, similar to the cut plot. It's going from around 25 psi to atmospheric. So that would be surface plots. So we're going to right click and hide that, but not before we show our geometry. And the next thing that we're going to go through is flow trajectories. And this is a big favorite for FloEFD users. It shows how the flow works, but if we want to show the flow, the best part is to animate it. So on the drop-down menu here, oh, if I did that too fast, let me go back. You right-click and you say Edit Definition, and this GUI pops up. And under Appearance, we go to Arrows Flat, and it's going to be with the pressure. We select that, and it shows how the flow runs. And if you right-click and select Play, you can create a nice video of how the flow is recirculating through the entire valve. Let's go back to velocity. So here we can see where the flow gets a little bit faster due to the area change. And we can see at the stagnation point how the flow recirculates. And this is super helpful if you want to know the dead spots of your valve. And you can also right-click and export to a video as well. So this is always a big favorite for FloEFD users, just because it looks really pretty. And if you ever get a different view, it's probably because you might have the lighting off. So you want to make sure that the lighting is on, especially if you do the pipes. So let's show that. And let's play. So yeah, these pipes have a nice 3D effect to them, and that's due to the lighting. So just make sure that you have that option there. And so yeah, you can see the recirculation here, and also going with the pipes as it recirculates in this area as well. So we're going to select stop. So just to recap, so we did computational domain, we went over boundary conditions, our goals, our global goals, checking the convergence, the mesh, we ran quotation marks and analysis, and we went through the mesh, the cut plots, surface plots, ISO surfaces, and we just did flow trajectories. So we're going to hide this. And the next thing that we're going to do, oh yeah.
Sorry, we have one more question from Tomas. He said, how all the surfaces were selected for the surface pressure plot, each picked separately by hand. So how did you select those?
The surface pressure plot. So the surface pressure is the surface pressure plot. Or is he talking about this section?
Which was each one picked separately by hand?
No, so what happens is that it's essentially where the fluid domain interfaces with the solid domain. So you don't have to select it. It's already created when you did that internal cavity. So that's why we want to check check the geometry to make sure we know what the fluid domain looks like, and that would be where our surface plot is. So as long as you make an internal cavity, that's how the surface plot is created. So you don't have to select the surfaces. The FloEFD will recognize it for you. I hope that answers your question. If so, I'll hide the surface plot. And then we're going to go, if you guys notice, we haven't left the NX environment whatsoever. We still have access to all the CAD geometry. So we're going to do that right now. Under application, we're going to go back to the modeling. Take a little while. And then we're going to select sketch 0. And let me do a front view. If you notice, we have so sketch 0 goes through the center line of the flow, and we're going to try to extract information from that center line. So I'm going to do Control-Shift-F, and it brings up flow analysis. So that's a little faster, and that's a natural hotkey that's already made with FloEFD. You don't have to set it. And for the X and Y plots, I'm going to show the velocity. And if I right-click under X and Y plots and say Edit Definition, I can choose pressure and velocity, and you can choose other ones, but since we're focusing on pressure and velocity, we're going to do that one and select Show. And it'll bring up these two graphs, and we can also drag this up in case we want to see it a little bit bigger. And what's really cool is that if you check out the center line, and if you drag your cursor on the center line, you can see the dot going through the valve, so you can actually mark and notice where the graph is in relation to your model. So if we notice, if this is a velocity cut plot, as the pressure drops, we can assume that the velocity is changing. So in real time, you can see it. So, and then here's another pressure drop, and there's a velocity change, and another pressure drop, and another velocity change. And you can also do that with velocity as well. And don't get this confused. To show these pressure and velocity graphs, to do that, you want to make sure that you right-click and select Show. Right-click and select Edit Definition, and then Show. If you select right-click and just say Show, it just brings it up right here, and then you won't be able to do the cursor. So yeah, just make sure you do the other way. So that, and also you can, edit definition, export these to Excel. So it'll actually open up Excel right for you, and those graphs that we had seen, it exports it. So you have velocity, pressure, and you also have all the plot data. All the plot data is there for you. So that's pretty cool. So cancel that. And the last thing that we're going to go through is our goal plots. So if you guys remember the goals that we set, let's go back and go into them. So we're going to right-click, Edit Definition, and these are all our goals that we had set. And we're going to select Show, just like how we did the X and Y plots. And we notice, okay, the question that we were asking was, what is the pump power that is needed to, or the pump pressure that is needed to maintain the flow rate of 10 gallons per minute? And that is, it would need a 10.57 PSI, and the inlet P is 25.25 PSI. And what's the force for the clamp in the X direction? It's around 5 newtons. And then the max velocity that we were wanting to know in the entire computational domain, which was for the entire model, was around 1800. So now the question is, where is that velocity? So if you guys remembered when we did cut plots, when we first created them, this maximum velocity showed up. All we have to do is right-click and say Show Plot Maximum, and zooming in, we see from this slightly pink dot, that's where the highest velocity maximum is. So what's nice about FloEFD, since it's embedded in NX, if you want to make that flow a little less harsh, you can probably even out these edges and make them a little bit smoother, and you could probably decrease the flow velocity. So that's our demo. Going back to the PowerPoint. Little back. So just an overview. What did we do? We learned how to do a project setup, and just like going from left to right in the NX toolbar. The next thing we did was check geometry. We did cut plots, surface plots, the flow trajectories that you saw and to the left that we can export it to a video, the X and Y plots where you can also export it to Excel, and the goal plots. So here's a case study from Renault, a car company, a French car company, and they are a FloEFD user, and they found that FloEFD was able to make one of their thermal engineers basically twice as productive, and it reduced their costs by 50%. They were able to front load their CFD much faster in the manufacturing process, and it saved them a lot of time and money. They were able to save about like $2 to $5 on each LED, so you can imagine for each car, that's a lot of money, and they're hoping to even reduce costs by another 50%. So if you don't believe us, you can believe them in how effective FloEFD can be for your designs. So in summary, we learned what exactly is computational fluid dynamics, and we learned that we can front load CFD without even leaving the NX environment. We learned the entire demo, so project setup, cut plots, all the cool information that you can change really fast. If you noticed, changing back from pressure to velocity was really quick with FloEFD, and we learned how to export all the data in case your boss ever needs the hard numbers. You can export it all to Excel. So with that, I will take it back to Andrea.
Thanks, Kelsey. Great job. So this is our next session in just a couple of weeks. So we do this the first and third Thursday, like I mentioned at the beginning. The next one will be a crash course in synchronous technology, really interesting topic. Daniel Rubio will be our presenter. He knows a whole lot about synchronous technology. So this is definitely a session that you will not want to miss. If you cannot make it on the 19th, go ahead and register anyway, and we will send the recording out to you after the session is over, and that way you can watch it on your own time. We'll be posting the video from today's session on YouTube today, so then again, we'll be sending out the link to you. You can pass it along to your friends and colleagues, and be sure to subscribe to our channel and follow us on Twitter and LinkedIn, and that way you are informed every time that we post something new to our YouTube channel. And most of you probably already know this, but we are a full service engineering support company. So if you are in need of services to address your demand for advanced engineering capabilities, please reach out to us. We have lots of really great engineers that can just be there to fill in the gaps when you need it, as well as we offer additive manufacturing. A couple of companies that we work closely with are Mark Forged and HP. And like I said, thank you so much for attending. Please stick around for about 30 seconds after the session ends. We would love to get your feedback. There'll just be a quick little survey with just a couple of questions. Love to get your feedback about today's session. Let us know how we did, what we can do to improve in future sessions. And thank you so much for attending and taking your time to be with us today. And if you have any follow-up questions, you can reach us real easily at info@saratech.com. And that's just a great way to reach us, and we can get your answers quickly. Thanks so much. Have a wonderful day.